chains of subalgebras. And this idea of chains of subalgebras will actually play a very important role. Sorry, I just want to switch off my phone here. Will actually play a very important role in developing the idea of dynamical symmetries. Okay, so now let's move on to this idea of what is a dynamical symmetry and how does it crop up, why is it important, and how can we use it. So let us consider some quantum system that you give me, and of course a quantum system always has associated with it some Hilbert space. It might be finite or infinite dimensional, and some Hamiltonian. And what I'll assume now is that this Hilbert space of the quantum system carries some representation. It may be reducible or irreducible, it doesn't matter, of a Lie algebra A, and that we can identify some chain of subalgebras, like A contains A1, etc., for this algebra A that we have on the Hilbert space of the quantum system. Then we say the Hamiltonian has a dynamical symmetry if we can write it as a linear combination of the Casimir invariants of the algebras in this chain of subalgebras. So here I wrote it as a sum over P. P labels the order of the Casimir operator, so it could be second, third, whatever order, depending, of course, on the ranks of the different algebras that we have here. The gamma, Pi, these are just numbers now that basically, well, they act like coupling constants in the Hamiltonian. So they determine the strengths of the different contributions to the Hamiltonian. The I, of course, here just labels the different algebras that I have. So I runs from 1 to small n, and P is the order of the corresponding Casimir invariant. So if this happens, then we say the Hamiltonian has a dynamical symmetry. So now why is this useful?
No, Frederik, just can I ask one question just to interrupt? So
yes.
this Casimir operator, they correspond to these subalgebras, is it? For each subalgebra, you associated Casimir.
Correct. So for each subalgebra, you will have L Casimir invariants, right? Depending on the rank of the algebra. So let's say we look at A1, and let's say that it's a rank A1 of the algebra, then I will have L1 Casimir invariants for this one. Similarly for this two up, down, up to A8. Yes.
Okay.
Okay. So please interrupt if you have questions. I can't see any, I don't see the screen or the participants that I'm forced my presentation. So just shout if you have any questions. Okay, now one thing to note, which is quite important here, is that the smallest subalgebra, this A8, is in fact an exact symmetry. It's a symmetry of the Hamiltonian in the sense that all the elements of the subalgebra AN will commute with the Hamiltonian. So, yeah, as you can see here, so if I take the commutator of the Hamiltonian with any x, where x is an element of the subalgebra AN, then the commutator is 0. That's basically trivial. It's by definition the case. Because remember that the elements of the subalgebra AN, which obviously they are also elements of all the higher algebras, subalgebras A1, A2, etc. And by definition, the elements of the algebra commute with the Casimir invariant. So by definition, the x, all the x's in the smaller subalgebra must commute with the Casimir invariants, of course, of the AN, the AN minus 1, etc., up to the A1. or actually
so again, let me interrupt you a little bit. So, for example, Partha was asking a question yesterday that if my Hamiltonian is valued in the Lie algebra, for example, if you in our one of our recent papers, we have said that if you consider the generalized harmonic oscillator, you have P square, Q square, and PQ term as well, or its symmetrized form. So they form the Lie algebra generators of SU11, the non-compact group SU11.
Correct.
So can we say that it is it also enjoys dynamical symmetry?
Yes. So one has to be a little bit careful. So let me let me phrase it this way. So the mere fact that Hamiltonian is written in terms of generators of some Lie algebra doesn't necessarily mean it's a dynamical symmetry. It must specifically be a linear combination of a linear invariance of the algebra and subgroup. So if you just write the most general Hamiltonian, let's take the case of harmonic oscillator where you have SU11. I will come back to that a little bit later. But let's take that case. So if you just write the most general, let's say second order Hamiltonian, the second order, the bracket in the generators of SU11, that doesn't mean you have a dynamical symmetry. It must specifically be a linear combination of Casimir invariance of SU11 and the possible subgroup. So when you write the most general Hamiltonian with the generators of some Lie algebra, you will not be able to solve that. To write down the eigenvalues of that Hamiltonian, that's not possible. But specifically when it is a linear combination of the Casimir invariance subalgebras, then you can actually write down the eigenvalues explicitly. Then it becomes soluble or quantum system. Did I answer the question?
Yeah.
I will come back. I will be very explicit about this a little bit later on, and then it should be a bit clearer. So, but besides the mechanism, you'll note here that I make the remark that the small an, the smallest subalgebra, an is the symmetry of the Hamiltonian. Of course, this will mean that the eigenvalues of the Hamiltonian are degenerate in the an. So if I have a certain state and I apply a generator to an, I will get something with the same eigenvalue. But of course, this is not a case for any other generator. So let's say I take for subalgebra, let's say I take an element from A2, for example, then obviously that does not commute necessarily with the element of the algebras lower down.
Your voice is breaking somehow. It's not always.
Yeah. Okay. I don't know. The sound seems to be. Maybe I should turn off the camera. Then normally the sound comes through. Let us try that.
Mr. Chakravarti, may I mute you because then the sound comes properly. Yeah. Yes, Professor Schultz?
I didn't hear you now.
It's a bit better, but still down.
Okay. Well, I haven't switched off the camera yet. Let me just see what happens if I switch off the camera.
You can switch on the camera. Actually, it is off already.
Is it off? It can't be. It is on at the moment.
It's for us. It's showing it's off. Can you please put it on and off again? I mean, just change it once.
Okay.
Sorry, I'm disturbing you.
There it's on now. The camera is on now, and the microphone is on.
Okay.
Okay. Can you see and hear me?
Yeah, pretty well. Better.
Okay, I think the reason, okay, so you should see somewhere, but the reason why you may not be seeing me is because I'm in presentation mode at the moment. Okay, let's, can you still hear me? That's the important thing. And see the slides, that's the important thing.
Slides are visible.
Okay. All right, so I'll try to speak a little bit closer also to the microphone, into the microphone. So let me again just emphasize that the smallest subalgebra AN, that will be a symmetry of the Hamiltonian, but if you look at the larger ones, then this will not be the case. So if you take an element, let's say from A2, that will not necessarily commute with the Hamiltonian. That should be very clear because it does not necessarily commute with the Casimirs of the subalgebras that A2 contains. Okay, so now furthermore, by construction, you can immediately see that if I calculate the commutator between the Casimir invariants of two different subalgebras, I and J, and it doesn't matter what the order is, then they will automatically commute. That is again by construction the case because either J or I will be contained in the other algebra, and then by definition all the elements and their Casimirs must commute. So these are then also commuting elements or commuting operators in the Hilbert space. So what we can do now is that we can then obviously write down the eigenvalues of this Hamiltonian if we know the eigenvalues of the different Casimir operators in the chain. So then we can write down the full spectrum actually of this Hamiltonian that I have here. I know the eigenvalues of this, and then if I have that, then I can obviously then, since these are commuting, I can then write down the full eigenvalue spectrum of the Hamiltonian. So this is the idea behind a dynamical symmetry, is that it allows us to actually solve the eigenvalue problem completely for certain classes of Hamiltonians. So once the Hamiltonian has a dynamical symmetry, we can explicitly write down the eigenvalues. And of course, we also know the eigenstates because we can label the eigenstates, like I described before, through the chain of subalgebras, like I have here. So we know not only the eigenvalues, but we also know the full eigenstates of such Hamiltonian. So you can see that this is a very useful situation. The only question is whether it is physically non-trivial, these different kinds of Hamiltonians, and I'll come back to that and discuss also then some examples for you. All right. There's another useful property or fact that one can use. So since we know the eigenstates and the eigenvalues and eigenstates of the Hamiltonian, we can also begin to compute things like transition amplitudes. And the way you go about this is you will write down physical observables, and you will write them down as tensor operators transforming in a particular way, normally under the smallest algebra, so the AN in this case, which is, as you will remember, an exact symmetry of the Hamiltonian. And once you have done that, you can begin to compute these transition amplitudes using the standard Wigner-Eckhart theorem. And of course, what you need to know then are also the Clebsch-Gordon coefficients. So of course, you have to calculate reduced matrix elements. You need to know the Clebsch-Gordon coefficients. So this, of course, is generally not so easy to do, but in principle, at least, you can compute such transition amplitudes, and you can write down selection rules, etc. Once you you know how your physical observables will transform under the smallest or under the symmetry group of the Hamiltonian. Now, what is also important to realize is that there are, of course, many different chains of subalgebras one can write down. So you can immediately see, well, you can't see it immediately here, but I will give you some examples. But you can write down, of course, if you have a very big algebra A, you can write down many different chains, even though these chains may end up in the same smallest subalgebra. I'll show you examples of that. So you could say, I want the Hamiltonian to have a specific symmetry. One example that I will demonstrate is rotational symmetry. You say, okay, I want the Hamiltonian to be rotational invariant. And then I can write down all the possible chains that ends up in a SO3 algebra. Because the SO3 algebra, if that's the smallest one, that will, by construction, then be a symmetry of the Hamiltonian. And so this allows me to actually investigate different dynamic limits of the system or the many-body system in front of me. Now, what is interesting about this, and I'll come back to this, is that these different integrable limits, these different soluble limits, are normally, not always, but normally they are separated by quantum phase transition. So if you were to change the parameters in Hamiltonian from one of these limits to another one, you will typically see that the ground state, at a ground state, you will either get a proper level crossing, or else you will get something which is called avoided level crossings. But the nature of the ground state will change quite drastically as you move from one limit to another limit, which is a signal of what we call a quantum phase transition. And as you may know, that the classification and the understanding of quantum phase transition is one of the challenges in many-body systems. And this gives us a useful way of actually investigating then different limits or different quantum phases of some many-body system. All right. Okay, this is what I just said. So let me emphasize also that if you look at the ground state properties, they typically have quite different correlations in them for the different dynamical limits or dynamical symmetries that you may have. So the bottom line of this discussion is really that your dynamical symmetric Hamiltonians are really fully soluble quantum systems. In fact, they are fully soluble, like I will demonstrate now immediately here after. They're actually fully soluble many-body systems. So it gives you really a constructive way to write down Hamiltonians that are fully soluble, and you can then, of course, also investigate the physical properties of these different limits and how you what kind of transitions occur as you move from the one to the other. One final comment I want to make is that you can also now, of course, you don't just have to stick to the precise dynamical symmetric Hamiltonian. You could are not pure Casimir invariants of the chain of subalgebras. And of course, then you can apply standard perturbation theory to calculate the effect of those. And now, if those terms that you add to the Hamiltonian, if those perturbations, again, are constructed as tensor operators, once transforming in a very specific way under your symmetry group or the different algebras in the chain that you have, then you can calculate, you can do the perturbative calculation quite systematically, again, just using group theoretical techniques. Because at the end of the day, all you need to do then again is you have to calculate matrix elements between states that you know how they are labeled, how they transform. This is the labeling that I mentioned, where you label the states using the elements of this, or the elements in the chain of subalgebras. And if the physical observable that you have transforms like a tensor operator, you again just apply the Wigner-Eckart theorem, and you can explicitly compute the necessary matrix elements and do the perturbative calculation and calculate how the spectrum of the Hamiltonian will be altered by such small perturbations. Typically, because there are quantum phase transitions separating the different dynamical symmetries, you cannot use perturbation theory, or your perturbation series won't converge. If you are at a certain dynamical symmetry and you add perturbations, then normally there will be a finite convergence radius, because the other dynamical symmetry is a non-perturbative effect, because there is in between some kind of quantum phase transition happening. All right, so you can see then also the benefit here. So these dynamical symmetric Hamiltonians really give us non-perturbative approximations or of the quantum system. You can't reach the one from the other just plainly through perturbation theory or perturbative computations. They really you need some kind of non-perturbative approach to go from the one to the other. Okay. Just one final remark about dynamical symmetries is that they don't, I will basically use them here in the context of second quantized Hamiltonians, but this is not the only place where they are useful, because you can, I think you all know that you can write down differential operator realizations of Lie algebras. So you can write down a very complicated differential equation, not even second, it could be higher order as well. And then you can actually identify dynamical symmetries in that particular case as well. So you can identify certain limits of this differential equation that are also fully soluble, where you can actually then also write down the solutions of this differential equation completely using your knowledge of the dynamical symmetry. So this also turns out to be a very useful technique in solving certain differential equations. One example that I can perhaps mention here is the now I've forgotten the name of the potential. It will come back to me, but in one dimension there's a very famous, it's also used actually in higher dimensions, but a very famous potential that is used to describe molecules, for example. If you write an Schrödinger equation, in that case it's a differential equation, you can use exactly these techniques. It's called a Morse potential, sorry. The Morse potential, then you can actually solve the differential equation for the Morse potential completely using exactly the same ideas. Okay, so let us talk about how these ideas are actually concretely realized in some many-body system. So what I will start with is some Hamiltonian, and you have now gone through the second quantization of the system. So, and you can then write your Hamiltonian, and this could be either bosonic or fermionic. And here I will write it, or I will consider only so-called one and two body interactions. So what this means is the Hamiltonian contains creation and annihilation operators. This is the one body part, and then the two body part, which is the interacting part where you have 2 annihilation and 2 creation operators. Now, in what I wrote down here, you will see that I have assumed, of course, particle conservation. So I assume that Hamiltonian does not change the number of particles. So there is not like 2 creation operators, for example, or 2 annihilation operators. So this is the standard form that you will have in some or other many-body system. But of course, if you do, for example, something like superconductivity, then in that case, when you do a Bogoliubov transformation, you may, of course, have that the quasi-particles are not conserved. So there you could, for example, have something that contains 2 creation or 2 annihilation operators, etc. I will show you in a moment that even in that case, you can still identify your dynamical symmetry. So the conservation of the particle number is not absolutely essential for the dynamical symmetry program to work. In fact, I will rewrite this Hamiltonian a little bit later into a different form, which explicitly demonstrates this idea. Now, so the first step I will do, in the first approach, I will rewrite this Hamiltonian slightly. So the first term is, of course, still there, the one-body part. But what I'll do with the 2-body part is I'll reorder the creation and annihilation operator here in the middle. So I'll switch the A beta dagger and the A gamma around. So I can do that, of course, just using the commutation or anti-commutation relations for bosons or fermions. Of course, if I do that, I will generate extra one-body terms. So this is why the epsilon here is different now. So I get the epsilon prime. So the one-body term will look different. But the 2-body term will then look the same, but just with these 2 operators switched around. Okay, now, all right, yeah, I just explained the notation. Something I should emphasize also here is that for the moment, I will assume that I have a finite number of single particle states. So the alpha, beta, gamma, delta, these labels on the creation and annihilation operators runs from 1 to, let's say, n. N can be very large. If you work with a system where you have an infinite number of single particle states, it becomes, of course, more complicated. And then one has to start looking at infinite dimensional Lie algebras or Katz-Moody Lie algebras. But I don't want to complicate matters at this point. So if you have, you can imagine then just introducing some kind of cutoff. If, for example, the alphas label momentum states, you can imagine you introduce some kind of momentum cutoff, and then you are just left over with a finite number of states. Of course, that is if the momentum is discrete, which would happen under certain conditions if you have finite volume or something like that. All right.
Excuse me, sir.
Yes.
Why the coefficient in the first term changes? Epsilon prime.
Sorry, can you repeat?
Why the coefficient epsilon alpha beta in the first term changes to epsilon prime alpha beta? The above equation.
Why are the epsilons different here and here?
Yeah.
Yeah. Okay. So the reason for that is when I look at this term here, all right, so I take the A beta dagger A gamma. I use, let's take bosons, for example, right? So then I can write the A beta dagger A gamma from the commutator as a delta gamma beta plus the other order. So the order A, right? So I see I get 2 contributions. The one gives rise to this, when the order is switched, but then I have a delta gamma beta also appearing. And you see that will give rise then to a modified 1 particle contribution. That will give, okay, so it will give a 2 particle part, and you will contract the gamma and beta indices, and that will contribute to the 1 particle part. So that's just a straightforward rewriting using the commutation relations.
Yes, sir.
All right. Now, what you will note now, if you look at this, is if I introduce the following n square operators, I call them G alpha beta, A alpha dagger, A beta. And alpha and beta runs from 1 to 2n. So this is now actually, yeah, this is for bosons or fermions that I can introduce these. Then they actually close, these operators close on a Lie algebra, which is Un. That's not very difficult to check. So there are a variety of ways of doing that. So I just make the statement here, but you can go and explicitly, by computing the commutation relations of these things, you can explicitly check that the algebra that comes out is exactly the algebra of Un, which of course has exactly n square generators. And this is the both for both fermions. If you now go back to this Hamiltonian, you change the order here, you can immediately see that this Hamiltonian is in fact linear. This is in these elements, or the elements, the generators of this algebra, and quadratic. So this is just a straightforward rewriting. And imagination Hamiltonian, where I choose the coefficients, the epsilon alpha prime, the epsilon prime, and the v's inside, is in fact a linear combination of the somehow the chain of subgroups. Well, it's not well, the linear combination of Casimir of Un. But in this case, you will see Hamiltonian is specific. So here it's only the so-called first order Casimir invariant or second order Casimir invariant that Hamiltonian. I should perhaps just make the remark here that you group of a first Casimir second order. I be a little bit more restrictive as well.
Frederik, you're not audible now. It's not audible.
I said, okay.
Can you just...
All right.
I think you are moving away from the microphone.
Maybe I should try to switch off the camera and let's just see if that
maybe,
improves.
maybe.
Let me just see. Okay.
Yeah, it's
can
audible.
you perhaps hear me now? Okay, it's better. I think there's I've had also this morning a bit of problems with the internet connection. So I think that's so if I switch off the camera, it gives a bit more bandwidth, and it should be a bit.
Yeah, this is better now.
Okay. All right. Okay. So let me just go here into full screen. All right. So, like I said, one may also want to prescribe that this Hamiltonian has a specific symmetry. And recall now that the smallest algebra was always a symmetry of the Hamiltonian. So what we can do now is to enforce the condition that this Hamiltonian, and specifically for physical reasons here, we look at rotational symmetry. So it must contain a SO3, or which is isomorphic, of course, the issue to subalgebra. So we can now consider all the possible chains of UN which contains SO3 as the smallest subalgebra. So we start with UN and we consider then algebras in between, and the final smallest algebra would be SO3. And if we can write a Hamiltonian, then in terms of the Casimirs of those in subgroups, then we have a dynamical symmetry and we can write down the eigenvalues completely. So here, for example, so what I'm writing is UN, and then I have, let's say, A1, A2 up to SO3, B1, etc. So each one of these possible chains will give me a Hamiltonian, which is completely soluble, integrable, if you want to use that word. Each one has a full rotational symmetry, and we have explicit formulas because in this case, you see, it is written in terms of the first and second order Casimirs of UN. We know the eigenvalues of those, so we can actually write down the eigenvalues of this Hamiltonian very explicitly and analytically. So this gives us a very powerful way of at least then investigating different limits of this very general many-body system that we have in front of us. Right, so this is simply what I'm saying here. So if I make a choice of the epsilons and V's, then I should be able to write this Hamiltonian as a linear combination of first and second order Casimirs. You see, so I runs from 1 to 2. I here labels okay, this is actually incorrect. I runs over the algebra, but over the subalgebras, but the order will only be 1 and 2. Okay, so we will have only first or second order Casimirs appearing in this Hamiltonian because the Hamiltonian itself is at most quadratic in the generators of the algebra. Right, and as I've said already, each one of these dynamical symmetries now represents a soluble many-body Hamiltonian, and each one of these generically correspond to a different quantum phase. So different kinds of ground states, and as we move from the one to the other, we will see typically avoided level crossings between the ground state and some of the lower excited states. This two-body Hamiltonian that I wrote down here actually has a larger symmetry. It's not just UN. So let me explain how you can get a larger symmetry. But before I do that, maybe I should just go back here one step, because I'm sure that somebody is worried about this. You will know that there's no distinction from the dynamical symmetry point of view here between the case of fermions or bosons. The Hamiltonian in both cases are linear and quadratic in the elements of UN. And if I write down the dynamical symmetry, the Hamiltonian in both cases will be a linear combination of first and second order Casimirs. So you may ask, so what's the difference between bosons and fermions here? So I don't know if somebody wants to try and give me an answer to that one before I give you the answer, but let me hear. Maybe somebody wants to try and give me an answer to that question. So what's different? What's the difference here between a boson and fermion system? Okay,
one is antisymmetric and the other is symmetric.
Correct. Yes, you're on the right track. So the point is that the Hilbert spaces, of course, are quite different. In the case of bosons, we are talking about symmetric representations of UN, and in the case of fermions, antisymmetric representations. So if you talk about in terms of Young diagrams, the one representation would be a full row, the other one a full column, and of course, if you then reduce with respect to the subalgebras, they are different, they have different content. So the important point here is that the representation content, from a representation theory point of view, the content of boson-Fock space is quite different to the content of fermion-Fock space. And this is why they have different spectra. So a boson operator and a fermion operator won't have the same spectra, because the Hilbert spaces, which is boson-Fock space or fermion-Fock space, contain different representations of the different algebras. So that's the important difference here. But you can see that it gives one also quite a nice unifying perspective. This perspective of dynamical symmetry gives you a rather nice unifying perspective between bosons and fermions, at least from the dynamical point of view when you write down the Hamiltonian. And it's only the representation aspect, the representations that are carried by the two Fock spaces that are different and makes the two systems physically different. Okay, now there's actually a bigger symmetry you can write down for these Hamiltonians, and this is the following. So if we, and here we have to now distinguish between bosons and fermions, but if I consider bosons, I can actually write down n times 2n plus 1 operators, which are pairs. So it's the A alpha dagger, A beta dagger. This combination, and then of course the adjoint, and also the number operators here. So you see the G alpha beta, this is already the UN that we had. So this is a bigger algebra because we add these generators also to the algebra. So this is a considerably bigger algebra which contains UN as a subalgebra. Now you can quickly again check, well, just straightforwardly, what you must be careful here about, of course, is that switching alpha and beta here doesn't give me a new generator because bosons commute. So I must only count here in these pairs, alpha large or equal to beta. And here, of course, I can have any combination, but you can quickly calculate that this is the number of operators that you have. And in fact, these operators span a very well-known Lie algebra as well, which is the symplectic Lie algebra SP2N. And again, if you go back to the original Hamiltonian, you will see, and you look here now, the first form that I wrote down, you can see that this is in fact also linear and quadratic in the generators of SP2N. So I can also view this Hamiltonian as being written in terms of generators of the SP2N Lie algebra, and linear and quadratic in those elements of the SP2N algebra. And now, just like before, I can now say, okay, we can now look at all possible chains of SP2N ending in SO3. Then again, I have a fully soluble many-body system in front of me with rotational symmetry. And of course, this offers me new alternatives to just the UN, the subchains of UN. I can now look at the subchains of SP2N as well. And like I mentioned before, and like you can see here, if I allow this possibility, I can even write terms in the Hamiltonian that do not conserve the number of particles. All right. And then it's still fine, because they are still linear and quadratic in the, if I only allow up to quadratic forms, of course, but it will still be linear and quadratic in the elements of SP2N. So for that reason, this when you look at SP2N, this allows you to actually construct non-conserving Hamiltonians or non-particle conserving Hamiltonians that also have a dynamical symmetry and that are also fully soluble, but you can still encode completely the rotational symmetry, for example. So this is very useful, like I mentioned, if you want to study, for example, superconducting systems or the phase transition between normal and superconducting, etc. So this is one example of where you can actually view the normal phase of a system or the superconducting phase as two different dynamical limits. If you talk about fermions, things are slightly different, because for fermions, of course, we have to keep in mind, if we form a pair like this, if the alpha and beta are equal, then this is just 0 because they're anti-commuting. So here we must only consider the alpha strictly bigger than beta. And then you can quickly check that you have n times 2n minus 1 such operators that you can now write down. And note again that you have the un here as a subalgebra. And you can check that these generators actually close on a Lie algebra of SO2n. So you see, when you look at a non-particle conserving Hamiltonians, then there is a distinction between bosons and fermions. The one would have a dynamical symmetry associated with sp2n and the other one of SO2n. But once again, now you can go through the same argument, write down chains of subalgebras that end, let's say, again in SO3 because you want rotational symmetry, and you can again investigate a variety of different dynamical limits of this Hamiltonian. And again, as I said, corresponding to different kinds of ground states and correlations in the system. So what I think I must do today, so let me see, where are we time-wise? Okay, we're already an hour basically into the thing. So what I will do now, and I think I'll do that tomorrow, is to then begin to construct or give you very explicit examples of this. And like I said, I will first start with a very trivial example, which is just a rigid rotor. And then discuss molecules and some applications to nuclear physics, and then also indicate how one can actually generalize this to mixed boson and fermionic systems, where there are some very interesting things that can also be done. But let me stop here for today, and then we can go on tomorrow. But let me hear, maybe there are questions again. Can you hear me?
Yeah, quite audible.
Okay, all right. Any questions?
Actually audible.
Hello, Frederik, can you hear me?
Yes, let me
Hi,
just...
this is Sachin.
Hi, Sachin.
Hi, how are you?
I'm doing well, and you?
Very good. I had a question, and I was wondering if you could comment about dynamical symmetries that occur in classical systems, and what we can learn about when we use the idea of dynamical systems to study classical systems. Now, I think some of the students may know that in classical systems, the most famous example of dynamical symmetry is for the harmonic oscillator or for the Coulomb problem. And so could you comment on the dynamical symmetries in the classical setting? Maybe it might help the students get a better grip of the ideas that you're discussing.
Yeah, it's very much the same idea, but normally I think if you look at the literature, it's normally phrased differently. But essentially, in classical systems, of course, you can construct certain quantities conserved in time. Like, for example, like I mentioned, if you look at a hydrogen atom, for example, you have the Runge-Lorentz vector, which you would normally not expect as a constant of motion. But of course, if you look carefully at the generators, I think the best way of doing it there probably is to look again at the generator of time translations as the Hamiltonian, introduce Poisson brackets, and then you can basically, once you're on a level of the Poisson brackets, go through essentially the same analysis as I did here for quantum systems. I think that would probably make it the clearest, or put it put it on a parallel track to the quantum analysis. At least that's the way I always try to do it when I talk about classical systems, is to do it in terms of the Poisson brackets and investigate the symmetries on that level, and in dynamical symmetries in particular. I don't know if I answered your question there.
Yeah, I think you did. I have one more question, which is that you mentioned that when you study dynamical symmetries, it is often easy to keep track of level crossings.
No, it's not. It's not so easy to keep track of the level crossings. What I would say is that when you have two different dynamical symmetries, you know, and you're not guaranteed, but you know that very likely you will see some kind of level crossing or avoided level crossing as you move from the one to the other.
Okay. So my question was, how important is it for the system to be infinite dimensional? Is it if you see level crossings in a finite dimensional system, then would you still call it, I mean, for example, if as you change a particular control parameter, if the nature of the ground state changes across a critical value, would you still describe it as a quantum or as a phase transition, if even if the number of degrees are finite?
Yeah. Okay, so that's a very good question, Sachin. So first, let me say that, of course, there are two things that can happen or two ways in which a quantum phase transition can occur. The one is through a true level crossing. Now, you know that this can only happen if you have like two subspaces which are not connected, let's say, due to selection rules. And then, of course, the eigenstates in the one subspace may literally cross the eigenstates in another one. If they're not coupled, then we can have true level crossing. So, for example, an excited state can cross the ground state and become the ground state. And if you follow, then in that case, the ground state energy, you will see it make a kink. It's continuous, but of course it makes a kink. So the first order derivative of the ground state energy will actually be discontinuous. So that would be like a kind of first order phase transition. So that's the one way in which it can happen. And that, of course, can happen in finite dimensional systems. There's no problem with that.
Okay. Except that this is not first order in the sense of thermodynamic, right?
No, correct. It's not first order in the sense of thermodynamic. I use that language here in the sense that the energy of the ground state energy, which would be the energy, of course, of the thermodynamic system at zero temperature, in the sense that the first order of, derivative of that quantity will be discontinuous. Now, the second thing that can happen is a more subtle thing. And that is that, in fact, that's quite a general theorem. So if you don't have this situation of subspaces that are not connected, so if you have a generic matrix that is filled up with entries, then and if you constrain the matrix to be a Mercian and you move along some axis or some parameter and the Hamiltonian stays a Mercian, then you can actually not get a level crossing. So two levels can come close, but they cannot cross because there's a coupling between them. This is a very famous theorem due to Wigner, actually. And this is where the term of avoided level crossing comes from. But what actually happens is in those cases you have, if you just go off the real axis, if you just make this parameter complex, you find that there is something called an exceptional point, which is very close to the real axis. An exceptional point is a point where two eigenvalues coincide. The Hamiltonian will then not be a Mercian, it will be a non-Mercian Hamiltonian, but two eigenvalues can coincide. And in fact, in that case, the eigenstates are linearly dependent. So, the eigenstates will also not span the full Hilbert space in that case. So this is what is called exceptional points. And what happens is these exceptional points come very close to the real axis in terms of this parameter you are varying. And when you pass close to this exceptional point, you see that the two levels come close together. At the exceptional point, they will actually join, but since you are not crossing the exceptional point, since it's in a complex plane, you're passing close to it, you will just see them coming close together and then they start departing again. But in that process, then the two states change their character as well. So the ground state, the upper state becomes basically the ground state, and the lower one becomes the excited state after you have passed from the past the exceptional point. Now, in that case, one would say, okay, this is not a proper phase transition in the sense that the first order derivative of the energy will not be discontinuous. But what happens there is exactly what you mentioned. If you now have a system and you increase the dimensionality, for example, the dimensionality of the matrix that you have with the Hamiltonian will depend on a number of particles. Now you pack in more particles, then you actually find that those exceptional points start to pinch into the real axis. They accumulate right on the real axis so that it actually turns in a thermodynamic limit into a proper phase transition. So you're quite right that there is a subtlety in identifying phase transitions, quantum phase transitions in finite systems. But the normal way we do it is to study the behavior of these exceptional points and whether there's an accumulation of the exceptional points at a certain critical value of a coupling constant. And if there is such an accumulation, then we would say it's still a quantum phase transition. One very nice example of such a model is what is called the Lipkin model. I won't discuss it here, but that exhibits a very nice example of precisely these kinds of quantum phase transitions. So I'm not sure whether, again, if I answered your question, but yeah, thanks for that question, Sachin.
Yeah, I mean, this is a question that requires extensive discussion. So we can do this after the students have asked you more specific questions about your talk, which I would like to add at this moment that I enjoyed very much.
Okay, thanks. Any other questions?
Yeah, the students have put some couple of questions in the chat box. So
okay, let me see if I can access that box.
Should I pick it for you?
Yeah, it's even better.
I have it. I have it here. Okay, so there's one question here. Can dynamical symmetry be related to any geometrical symmetry?
Yeah.
Or does it always indicate some physical symmetry? Okay. I'm not sure. I don't think we can. Well, I'm not aware of any connection directly with geometrical symmetries. It depends also on what one exactly means now with a geometrical symmetry. I would also, I mean, let me say the following. When you talk about the physical symmetry, it does not imply. I must emphasize this again. So a dynamical symmetry doesn't imply a symmetry. So if the Hamiltonian is a dynamical symmetry, it doesn't mean that you have a true symmetry. It's only the smaller subalgebra that actually represent the true symmetry of the system. This situation. The dynamical symmetry rather has to do with the particular choice of parameters in the Hamiltonian, such that you can write this Hamiltonian in terms of the Casimir invariance of some chain, and once you have that, then you can actually, it's a soluble system. So I roughly put, it's a clever choice of the entries into a big matrix such that you can actually solve the eigenvalues of that matrix analytically and exactly. So if you want to think about it this way, it's doing the eigenvalue problem in the reverse order. I could have asked you the question, can you write me big matrices for which you know exactly what the eigenvalues would be? And of course, you can do some trivial things like writing a diagonal matrix and things like that, but we would like to do something a bit more fancy. And this gives you actually a way of doing this. This actually gives you a constructive way of writing down very big matrices. And despite that, you are actually able to write down the eigenvalues of these matrices exactly and analytically in many cases. I will actually give you tomorrow an example where I will write down the eigenvalues very explicitly for a rather complicated problem, and where you can see this. But and in addition to that, you have the nice feature that you can decide if you want some kind of symmetry built into your problem. So you can decide, okay, the Hamiltonian must possess this particular symmetry, and then you can investigate only the possible dynamical symmetries that are allowed by that particular symmetry that you impose, like rotational symmetry. It could also be other kinds of symmetries. There are some interesting applications also with even discrete symmetries that you can investigate. But these things, of course, play a very important role nowadays. For example, if you think about things like topological insulators, etc., where the classification of these systems depend very much on the symmetries that you are putting into your system. So one can investigate all these different scenarios. Okay, so here's another question: how to analyze temperature dependency in molecular vibrations in Lie algebra. So this is an interesting one again. So of course, if you have a dynamical symmetry, you know the eigenvalues of the Hamiltonian, and then of course you can write down the canonical partition function, which is trace e to the minus beta h. You can write down the partition function explicitly. And once you have that, then of course you can study the full thermodynamics of the system. You will, of course, not on that level. Well, I don't think you will see, I'm talking under correction here, I don't think you will see any kind of phase transition, thermal phase transition, so as you increase the temperature. But of course, if you now again change the parameters in Hamiltonian, so you use, instead of one dynamical symmetric Hamiltonian, another one, then of course you will have two completely different, in general, different partition functions. And you can then try to understand a link between these different partition functions, and that should actually encode information about the phase transition between the two situations as well. So you will go ahead and, so to answer the question very explicitly, you will go ahead and analyze the system in the standard way that you do thermodynamics. The only advantage here is that you can actually explicitly compute the partition function if you want to do that. And this has been done in the literature, particularly in the context of nuclear physics. Let's go to Partha. You have asked another question. Whenever a system Hamiltonian expressible in terms of linear combinations of some Lie group generators, then system Hamiltonian is always commute with the Casimir of the Lie algebra. Therefore, can we say system has dynamical symmetry? It is true, of course, that the if you write a Hamiltonian in terms of the generators of some Lie algebra, it will by definition commute with the Casimir invariant of that algebra. But that's not very useful, because all the states, all the eigenstates will be labeled by the same number. It doesn't give you any information about the dynamics. It's only when you have smaller Lie algebras, like in a chain, that you begin to learn something about the dynamics, because then you know that that there are different states in the Hilbert space with different energies, etc. So the you could call this, if you want to, a dynamical symmetry, but I would say that that's a very trivial form of dynamical symmetry. If you just look at the Hamiltonian written in terms of some generators and ask about its commutational relation with the Casimir. So in that sense, it's not very useful. And it's only if you start looking at subalgebras that you really begin to probe the dynamics. Okay, here's another question. We know that the hydrogen atom problem has, apart from the usual rotational, the SO4. Actually, I think it has a SO4-2 symmetry, if I remember correctly. Yes, so this is in fact the it's the biggest symmetry of the hydrogen atom. Sachin, you must correct me if I'm wrong, but if I remember correctly, it's SO4-2. That's a full dynamical symmetry of the. Well, in that case, I should perhaps say that people often don't use, in the context of the hydrogen atom, for example, they don't use the term dynamical symmetry necessarily. They will often use the term of a spectrum generating algebra. Yes, so in that case, it is essentially the same thing. What happens in that case is you can start with any eigenstate of the Hamiltonian, and by applying the generators of SO42 to it, you will generate all the possible eigenstates of the Hamiltonian. So literally you can ladder between all the possible eigenstates of the Hamiltonian using the SO42 group. SO4 itself is too small. You don't reach all the eigenstates. As you can imagine, because SO42 contains SO4, so if you have an irrep of SO42, then it will generally be reducible if you break it down to SO4. So you can only reach a subspace of the eigenstates using the SO4 generators. While if you use the SO42, if it's irreducible, the representation, you can actually reach all the possible eigenvalues, and that's or eigenstates, and that's why we call those then spectrum generating algebra. So the term of dynamical symmetry and spectrum generating algebras can be used interchangeably. Sometimes there are slight differences or in terms of what is meant, but it's more or less on the same footing. Are there any other questions?
Hello.
Yes.
Hello. Yes. So my other question is, can we derive the conserved quantity due to the dynamical symmetry using the Noether's law? No, sorry, Noether's theorem.
Oh, can you construct the conserved quantities using Noether's theorem?
Yes. Is it possible?
Okay, I'm not 100% sure about this now.
Because we are familiar the concept just due to the space-time symmetry using when I discuss the Noether theorems.
Yeah. So yeah, we are not busy really with a field theory necessarily, or at least if you do normal quantum mechanics, you will be working with 1 plus 0 dimensional
field theory.
So I'm not quite sure in what sense you can apply Noether's theorem here, but what would be interesting, and I have, frankly, I'm not sure that this has been done or investigated. I haven't done it, certainly. I'm not sure whether one can apply the ideas of dynamical symmetry in the context of field theories. Sachin, maybe you know something about that. I'm not sure about that.
Yeah, I think you can. But I would like to sort of roll back a bit and answer the question that was asked. Whether you study classical mechanics or quantum mechanics, a modern viewpoint is to look at the action, or
yes.
Or if you like, the Hamilton's principle. So if you look at the action, then you can look at variations of the you can look at variations of coordinates and velocities, or if you're looking at the Lagrangian, or variations of coordinates and momenta if you are looking at the Hamiltonian version. And you can study the equivalent of dynamical symmetries. I'm trying to remember a reference, but I have seen a derivation of the Laplace lens vector, which is a dynamical symmetry of the hydrogen atom, starting from looking at the action for the hydrogen atom.
Yeah.
So, sorry, Frederik, what did you say something?
No. In principle, I fully agree, Sachin. In principle, you should be able, by studying symmetries of the action, you should be able to uncover the full spectrum generating algebra actually from that.
Yes.
Regarding the infinite dimensional case, I don't have any. I can't think of any examples right off the top of my head, but I imagine that integrable models, at least in 1+1 dimensions, may come under this class that Frederik has in mind, and perhaps some of the perhaps the conserved quantities, the conserved charges for integrable models in 1+1 dimensions may you may be able to derive them through some kind of Noether-like argument. Although I'm not, I must say that I can't be. I'm not 100% sure about this.
Okay.
Yeah, I haven't seen it, but I would guess it is possible.
Okay. Thanks for the clarifications.
Okay, anything else?
Professor,
Yes, Shamit Bichar, go ahead.
in particle physics case, we see that the Hamiltonian that respects some symmetries, the ground state does not respect the symmetries. Then the quotient rule, from this quotient rule, we can form or something Goldstone bosons, right? In this dynamical case, when the Hamiltonian respects dynamical symmetry, the ground state may not show that symmetry, or the symmetry may be hidden. And can we infer something in like massless bosons or vector bosons, or number of these bosons from this dynamical symmetry perspective?
Okay, I'm not quite sure that I understood the question, because the sound was a little bit bad on my side. But if I understand you correctly, you are asking whether we can see something like spontaneous symmetry breaking.
Yes.
Yes. So certainly, in fact, the examples I will present next or tomorrow, there are examples where the ground state certainly does not necessarily have the symmetry of the Hamiltonian. So sure, you can have such kinds of spontaneous broken symmetry. So I don't know if that answers your question. It wasn't quite clear to me that was what you were asking, but that's what my response would be at this point.
Frederik, I think the question had a second part, which is that if it is
I
true
was
that
concerned about number of the bosons. If the symmetry is spontaneously broken, then what's the difference between the general Hamiltonian that preserves the symmetry and the dynamical symmetry? What will be the difference?
Well, let me phrase it this way, that you can have a Hamiltonian of a dynamical symmetry that breaks some other symmetry, or for which a ground state breaks a symmetry. So I don't think the existence of a dynamical symmetry excludes the possibility of spontaneous symmetry breaking. Let me phrase it that way. Sachin, maybe you understood the question better. I didn't quite get
I think the question was about whether, in particular, whether you see the analog of Goldstone bosons when a dynamical symmetry is broken by the ground state.
Yeah. Well, for sure that will be the case, because if the ground state breaks some other symmetry, and it could be a Hamiltonian of a dynamical symmetry. If you look at its ground state, it doesn't have a certain symmetry. Could be rotational symmetry or some other symmetry. Let's take a rotational symmetry. Then obviously, if I apply a generator of that symmetry group to the ground state, I will generate another state of the same energy. Of course, if that commutes with the Hamiltonian, so if the Hamiltonian has that symmetry, it must have, like I said, then it must imply some degeneracy. So the generators of that symmetry group will, in a sense, act then like a Goldstone bosons. So you will have flat directions, if I can phrase it that way.
Okay. Thank you, Professor.
Okay, it seems like there are no further questions.
I think Like anyone having any question, any more question?
Well, I just wanted to chat with Frederik about very interesting subject that he's talking about, but we can do it. We
Yeah,
can
you
do it
can carry
another.
on. If he doesn't have a time constraint, you can please carry on. But the
I have a
students, I don't think they have any question anymore.
okay, good.
Frederik, do you have any time constraints?
Not at the moment. I have about another, let me see, half an hour. Then I have another meeting, that I have to go into. But
yeah, my questions are not that deep that it will take half an hour.
okay, no, we can certainly chat. No problem.
So the question is, I guess the question is, what happens if you have a discrete symmetry, and the
Yeah.
discrete symmetry is broken by the ground state? And
Yeah.
I mean, this question is not, I'm not just asking as a technical legalistic question, because I think these are the kinds of situations that occur in study of the Yarn-Teller effect.
Yeah. Yeah.
So if I have a continuous symmetry that is broken, then we might expect some Goldstone mode, some
You will
analog
have
of
Goldstone mode. Yeah.
we will have some something like that. But if a discrete symmetry is broken by the ground state, then which is what might happen which is kind of the kind of thing that happens for certain kinds of molecules in the Yarn-Teller effect, right?
Yeah. Yeah.
So I was just wondering if you had any thoughts about what one might say about the ground states, or whether there are multiple ground states that are related by action of the discrete symmetry group, which is now unfortunately broken.
Yeah. I'm not sure about that one. I think we discussed this at some point. But
Yeah, no, I was just thinking aloud. I mean, it's a
yeah,
little bit
yeah, yeah.
unrelated to the development you have been presenting in the last two
Yeah.
lectures. So.
Well, look, so let me just understand. If I have a state, let's suppose I find a ground state of some Hamiltonian. The Hamiltonian commutes to some operator, a discrete symmetry. Let's say time invariant.
Or it could be even some crystalline symmetry,
It could be some crystalline symmetry, but
SO3, some subgroup of SO3.
Yeah, some discrete. But if I take that,
chain also contains some discrete symmetry, one-dimensional, Ising model.
Yeah.
D2 symmetry is a discrete symmetry.
But Sachin, I think what should happen, if I'm not wrong here now, is that you must find more than one ground state, and actually, I think the set of ground states you find must transform in some representation of this finite group that you have. So, because simply take any one of the ground states. Let's say, suppose you have found a ground. You have the ground state. Then just apply an element of this discrete symmetry. If you commute with the Hamiltonian, you end up with another ground state. Unless, of course, this ground state is invariant. If it's not invariant, you must end up with another one. And it must still be a ground state. So in this way, we can generate a whole discrete set of ground states. So it will not be like a Goldstone boson case, which is continuous actually, but it must be a discrete set. And you should be able to classify them, of course, then in terms of because they must obviously form an irrep under this finite dimensional group. And you should be able to classify these classes of ground states through the finite dimensional irreps of this group, which we know how to do. We actually use the permutation group to do that classification. So I think it's fully possible to do that, and it may even be neater than the Goldstone boson case.
Well, that's interesting. What you said is interesting. Yes.
So it would be interesting to have an explicit model. I'm not aware. Actually, you mentioned a couple of examples, but I'll have to look at that. So I'm actually not aware of a very nice example where you have that a ground state breaks a discrete symmetry.
I have to go back and look at this Yarn-Teller effect, which I think many molecules display. This was, first discussed by Jan and Edward Teller. But if I, it basically came out of some argument between Teller and Landau.
Yeah.
And there is I mean, let me not say anything more before I before I go back and look at, get a better control on what my understanding of this Jan-Teller effect. But my naive understanding is that the ground state of the molecule has lower symmetry than than what you naively expect by looking at the crystal structure or something.
Yeah,
but what you said is actually very interesting, because it seems to have, you talked about these exceptional points, and these as soon as you have exceptional points in the system, then you can have geometric phases.
Yeah, sure.
Right. So, I mean, the kinds of things that you're talking about is actually quite sophisticated, because it has, it has lots of implications. It has implications for geometric phase. It has implications for entanglement. And
well, there's another interesting link, of course, particularly if you take the geometric phase point of view, which is to topological insulators. So
that's right. Absolutely. Yes.
So
sorry, go on.
Where you don't necessarily break a symmetry, but you still have different phases, literally. And in that case, of course, you need to look at a different classification scheme, which is the topological route that you take in that case. So, and of course, so the interesting link here is, so when you have different topological phases, of course, when you move from one to the other, you actually encounter quantum phase transition in between as well. So there's an interesting link to also to this idea of dynamical symmetries, in the sense that you may ask the question, does the different dynamical symmetries actually correspond also to different topological phases? Because they are necessarily separated, well, not necessarily, but often separated by a quantum phase transition. So there are many different interesting things coming together here. To be quite frank, I think this whole idea of dynamical symmetries hasn't really been fully exploited. And
yes, I agree. It's one of these things which is just like a low-hanging fruit waiting to be plucked.
Yeah, no, that's my feeling as well. It was sort of a very popular thing, particularly molecular physics and nuclear physics in the 1980s, 1990s. Still
that's right, yes.
About mid-90s, then it sort of petered out. Yeah, it seems that people did not really try to take it to its full conclusions. And there may be some very interesting issues still lying around here.
Right.
Okay, so any further discussion? Vishwajit, anything from your side?
No, I really enjoyed the whole talk and the discussion. I don't have much of idea about these things, but it's really nice to listen to you talk and learn things. Let's look forward to some explicit example tomorrow.
Yeah. I will do at least a couple of examples, explicit examples tomorrow. Unfortunately, I can't go, of course, through all the calculational details, but let's see. I think we could get a gist of it
That'll be
rather quickly.
Yeah, the examples would be very nice, actually.
Yeah. Okay.
So Frederik, it was very nice to listen to your talk. I look forward to it tomorrow as well. And I'm sure that there will be a nice discussion at the end of your talk tomorrow.
Yeah, I hope so. And I hope to join you guys maybe next it goes on next week, right? The
Yeah,
workshop.
till 11.
Through the week, yes.
Yeah. So unfortunately, this week has been total chaos in my side because of this administrative job that I have. So I wasn't able to join, but next week I hope to join you, join for the other talks as well. So I'll see what I can fit in.
Frederik Lizzie is talking tomorrow.
Yeah, tomorrow is again unfortunately completely booked out on my side, Bishojit.
Okay.
I'm booked from 9 o'clock tomorrow morning till then this talk, and then after this talk I have another meeting till 6 o'clock tomorrow after. So today also. So it's.
So it seems that you are as busy as you were during your when you were director of the NITER.
It's even worse. It's even worse now, and I tell you why. It's because of COVID. There are so many things going wrong, and they have to be sorted out. So it's not normally the case, but COVID has worsened things, and of course